will appear at the stage twice. So it is Aaron Forde who will first give brief introduction on the correlation functions, and then he will have a break, and then he will tell about electrodynamics.
So usually go through these presentations, we usually jump from making couplings to RRR files, but there's usually one more step in between, and that's making correlation functions.
There is slide advancer.
Oh, right here.
Okay. Escape.
Oh, okay, so just very brief technical details. So I didn't know what a correlation function was until like a year ago, so I assume like a lot of undergraduates might not know. So basically it's just a measure of how similar a quantity is in space and time over different time periods. So like if you have one function at time t and you have another function at t plus like a dt, and it just measures like how similar they are at different times. And they don't have to be different. These can be like f and f, and that would be an autocorrelation function. That's usually what we do. And so the big deal is we use autocorrelation functions because rates of electronic transitions you can use those to, or you can use correlation functions to determine rates. So this guy's a rate, and then this guy here is a fancy way for autocorrelation. Essentially, like if you go through a textbook and read it, all this contains like information from Fermi's golden rule. So it's just another way to write Fermi's golden rule. So that's why we have.
What's the difference between correlation and autocorrelation?
Autocorrelation is how it measures its similarity with itself in time or space, and a correlation function necessarily doesn't have to be with itself. It can be with another function.
So if we change it to G here, it will be autocorrelation?
Yes.
And would you agree or disagree that there should be some exponential with time?
I won't disagree. Okay. So yeah. So and then this is just a nice way to visualize what an autocorrelation function does. So this first plot is just a plot of an autocorrelation of a Wavepulse. So how do I?
Oh,
it's still on the marker.
To draw?
Yeah, it's still on the marker.
Okay.
There we go. So this is the plot of an autocorrelation function, and then let it go a little bit. So these are two wave pulses. So at t0 they're on top of each other. So you start out initially at 1, and as you go through time, the wave pulses go out of phase. So you get negative correlations because you're multiplying a positive and a negative number. So you get a negative number. Go through again. They come back into phase a little bit. So you get a positive number again. They go back out of phase. Then after some time, they don't know each other anymore. Then if you plotted those...
So your autocorrelation is, or correlation is red times blue and integrate over the whole space.
So yeah, you basically just add it up at each time step.
Okay.
And then keep going. Then yeah. So if you plotted the values of the integrals at each point, it would do something like this. So this is in phase, out of phase, somewhat back in phase, and then this, they have no idea they're next to each other anymore.
Nice.
And so to make autocorrelation functions from the wave cars that we use, so the MATLAB code is pretty standard. It hasn't changed at all since I've been here. Correlation V3H, and you have to give it coupling, or all the coupling files that you generated. And then you just need energy pop, and you may need overlap, you may not, I can't remember, but I just usually put it in there anyway, because you need it eventually. So you feed it in these files, and it outputs some correlation functions of orbitals with each other, and basically takes all those correlation functions and converts it into an RRR. And to run the code, it's pretty robust. Basically all you have to input is some specifics about about the orbitals that you're using. So you enter your HOMO, max and min from your input overlap, and sometimes you just have to change like these loops just to load in the coupling files, depending on how many you have. So if you have 1,000, there's another loop below this that goes up to 1,000. And if you have less than 1,000, you just have to tell it which number or else it'll yell at you. And so if you run the script and it runs pretty healthy, this is a pretty typical figure. So it starts out at 1, decays very quickly, and then kind of oscillates. And then each of these colors are one of those core underscore homo files. So these are just correlations of autocorrelation of orbitals. Ones near the gap anyway, which are usually the important ones we look at. And that should be it.
So can you go back to this last slide? Let's thank Aaron just in case. And, if we remember presentations, well, some of us made presentations, remember presentations by Levi on dephasing, especially Javid should remember it. Their autocorrelation functions were decaying much slower. So what's were the dephasing autocorrelation functions presented by Levi and autocorrelation functions presented by Aaron applied to the same type of functions or to different characteristics?
So I've always assumed that dephasing was between different pairs of orbitals. So yes. I don't know, for Redfield tensors, they have I, J, K, L. So dephasing would be like the time that I and J are dissimilar from
so
K and L.
Which function, autocorrelation of which function are you showing here?
So you say the black one is like homo and homo minus 1.
Autocorrelation of nonadiabatic coupling.
Yes.
Your couplings file.
Yes.
Okay, and Levi and several other people, dephasing were applied to energy of orbital. So not the coupling, not the transition, but just energy of orbital, how it slowly changes in time. Mm-hmm. And autocorrelation between orbitals, and correlation between couplings behave on very different time scales. Okay. For orbitals, it lives for like 10, 20, maybe 50 femtoseconds. For couplings, so the main feature in this figure is that everything drops rapidly within 1 or 2 femtoseconds. So there is no correlation. The couplings, as Aaron defined, do not know about each other after a couple of femtoseconds. So the system has no memory.
So I'm just wondering why isn't it better to look on the fast Fourier frequency rather than looking on the autocorrelation functions?
Well,
it will be white noise.
Then, but you can see the frequency, how is the overlapping, the same frequency or different frequency. But in this case, what is the quantitative result from these autocorrelation functions?
Well, mostly this quantity here is what we're interested in.
I mean, how can you interpret this, what's the word, vibration, or this quantitatively?
So you can see initially at some time it decays really quickly, and then over time they kind of come back into phase with each other. But if you run this long enough or you get good enough statistics, over time they should average out to 0. So like this is just like, view it as statistical noise.
The reason for these oscillations is accumulation of electronic phase, and electronic phase accumulates really quickly on like attoseconds. So if one would redo this figure on the fraction of femtosecond, like doing it from 0 to 1 femtosecond with step of 1,000 steps, one would see continuous function with slow decay and maybe analyze it somehow. But this ultra short time ranges are not yet in our focus for practical applications. If one would model the free electron X-ray laser for sub-femtosecond processes, one would do modeling on the really short time steps.
But if we take FFT of this autocorrelation function, FFT, I mean fast Fourier transform of these autocorrelation functions, which one would be more convenient to read this information? This one or of FFT?
Well, which information?
I mean, for us looking on how many different frequencies involved on these things.
Unless you can visualize Fourier transforms in your head. Like you probably couldn't do it from this, but I mean you can.
In order to do Fourier transform, you need to shorten the time step 100 to 1,000 times. At this resolution, it is almost like a noise.
Okay.
So the only importance is the absolute value of couplings when they are laboring in time.
Any other questions?
More questions to Aaron? If no, then thank you once again.